both the graph responding to the constant net force and the graph representing the variable net force represent the same impulse acting on the baseball. Which geometric properties must the two graphs have in common? Area?
Yeah. So that's kind of saying, in reality, the graph wouldn't be just a constant force. It would kind of be like this. But what happens is this area would be the exact same as this area, because they have the same impulse.
Assume the pitcher throws a baseball so that it travels in a straight line parallel to the ground. The batter then hits the ball so it goes directly back to the pitcher along the same straight line. Define the direction the pitcher originally throws the ball as the positive X direction.
So kind of got a pitcher, he throws the ball in this direction, and this is positive X.
The batter hits it back.
Yeah, and then the impulse happens here, and he hits it back this direction.
So it would be negative.
So the impulse on the ball goes, but that would be, yeah, be the negative X direction.
Now assume that the pitcher in the part D throws a .145 kilogram baseball parallel to the ground with a speed of 32 meters per second in the positive X direction. The batter then hits the ball so it goes directly back to the pitcher along the same straight line. What is the ball's velocity just after leaving the bat if the bat applies an impulse of negative 8.4 newtons to the baseball?
That's Newton's seconds?
Yeah, seconds.
So that would be, so a Newton
So yeah.
is kilogram meters per second squared. So everything we do in impulse is just a kilogram meter per second. So that's equal to a Newton times second.
Okay.
So this is how you set these kinds of problems up, is you have a before then this is your impulse, and you have an after. And then you just add your impulse to your momentum before.
Oh, okay.
To get your after. So
You just do 32 minus 8.4.
not exactly, because 32 is your velocity here. So what's the momentum that you have before?
Momentum. You do 32 and then divide it by 145.
You wouldn't divide by, momentum is mv.
Oh, so you multiply
Yeah,
it.
you just multiply by 145, it's 32. And that would be your momentum initially. So what does this end up being?
145 times 32.
Okay? And the units on this would be kilograms times meters per second, right? Which is the same as this one. So this was your momentum before, and there's an impulse. An impulse is a change in momentum, and this would be your momentum after.
Okay.
So if you were to write this out, you could say momentum before, so momentum initial, plus change in momentum, or J, equals momentum after. Make sense?
Yeah.
Just because the change in momentum equals J equals P final minus P initial. So, what's our initial momentum?
4.64.
And then the change in momentum?
Negative 8.4.
And then what will this be?
Be negative.
It will be negative, yeah.
Negative like 3 point something.
Yep. Something like that.
Negative 3.76.
So is that the answer to the question though?
Oh no, because that's just momentum.
Right. So this is your momentum final. So how do you find velocity?
You times that by 0.145.
This time you'll divide it, right? So you have negative 3.76 equals your mass times velocity. So it would be 0.145.
Momentum, right?
Velocity. Yeah. So this is your momentum final.
Right.
You know your mass didn't change. You just know the velocity changed. So if you take this, divide by 0.145, that'll give you your velocity.
So it's negative 25.931.
Negative. Oh, okay, yeah. And if you look at your momentum before, it was going faster, right?
Right.
And it had a higher momentum. So your momentum dropped down to a magnitude of 3.76, so your velocity had to drop a little bit too.
It's a lot easier than the forces.
Yeah. There's another way to do this too. They'll do sometimes, like the book shows it, they call it momentum bar charts. And it's just where you plot your momentum. So this is P. So initially you've got 4.64. This is your initial. Then your impulse is negative 8.4. And these momentum bar charts have to add up to be 0. So then you know that your P final is going to be whatever you need to add together to get to those, right? So, wait a minute. That's not working out right. Oh, no. They don't add up to be 0, sorry. This, then you add this to it, and it'll give you your final. So this would be negative 3.76. So you start with your initial, you add your impulse to it, and then you give you your final. And the book talks about it a little bit, but it's just as easy to do it the other way. This is just a way to visualize it. So you can see that like this area, if you move J up here and moved it down like that, it would give you this.
Okay.
It's like whatever's left over, you know, that you add them together. So the same thing would work if, say, you had a positive J. So maybe this was going along at a certain speed and then you got hit from behind. Then you'd have a positive J, and this is like 9. Well, your final momentum would be greater.
And it would be those two added up?
Yeah.
Okay, so it would be like 13.64.
Yeah, exactly. So it's pretty straightforward.